Excellent. I'm just going to Excellent. I hope everybody can hear me on the Zoom, and thank you for those who are attending in person. Today, we have Professor Felipe Jornada, who is a professor here in the Material Science and Engineering Department at Stanford. Today, we'll be talking about understanding excited states, including materials. Just a brief introduction for Professor Jornada. He holds a physics in PhD from UC Berkeley, where he worked with Professor Stephen Louis on understanding the electronic and optical properties of 2D materials using first principles computational approaches. His work at UC Berkeley was awarded the Best Thesis Award from the Kavli Institute. And then he was a postdoctoral researcher at Lawrence Berkeley National Lab prior to joining Stanford. At Stanford, his research group is interested in advanced simulations for applications in energy research, physics at reduced dimensions, something that we'll hear about today, and quantum information. So yeah, without further ado, Professor Jornada. Thank you.
Thank you so much, Miguel, for the very kind introduction. Thank you for the invitation, and thank you all for coming here. I'm really excited to tell you some of our recent work on 3D materials and their application for quantum information, quantum science. Actually, perhaps I'd like to start with a perhaps larger overview of the problem that we're doing, how we typically do this in physics and material science, and what are some new perspectives that have really been emerging in the last few years for designing new materials. So, in the traditional kind of paradigm for materials, if you want to create a new device, say solar cell high efficiency, what one typically has to do is go back to the periodic table and raise a crystal and think, what are the crystal arrangement, atomic arrangements that gives the functionality that we're interested in? And to some degree, the same thing has been quite useful for quantum materials. So if you're interested in realizing a qubit or a spin system, we typically go back to materials and think, what is the realization of that particular quantum system by tailoring the atomic positions in the material. But what I want to say to you today is that there are actually two qualitatively different ways that you can realize these systems. There is not necessarily tailoring the individual position of atoms, that is actually quite powerful. One of them is that you can actually create materials not by necessarily changing the atomic positions, but by driving them out of the field. There's actually a lot of excitement about having light-driven phase transitions. Here at Stanford, of course, a lot of excitement about time crystals, where you can change the ground state by putting a material in cavity and sending polartons and so on. So basically, shining light and driving the material is a way to get qualitatively new phenomena and functionalities. And the other direction I'm going to mention is that also a new way that is quite powerful is to think about a material as almost as a metamaterial or as an emerging material that is dictated by a length scale and physics that is much larger than the length scale of the atomic positions and the individual in itself. And that is, of course, behind all the excitement in moiré materials, where you spectrum materials with defined twist angle, you have a pair and a pattern that is getting much larger than the individual supercell, unit cells, and that may support emerging properties from superconductivity, ferromagnetism, and correlated physics in general. So since I joined Stanford in 2020, right before the pandemic, maybe I can give you just a quick overview of what my group is up to, how we deal with those sort of problems, and how we can make progress in this field with our methods as well. So our group is computational and theoretical. We predict the materials and optical properties. And you may recall or may know of one very powerful technique known as density functional theory that is actually usually solved in the following way. One solves an effective Schrödinger-like equation known as the Quantum equation for orbitals. And the solution of such equations give you Lagrangian multiplier in orbitals that describe the ground state properties of materials, such as laser property, structural, magnetic, phase transitions, and so on. However, if you're interested in materials that are excited, mainly if you're interested in spectroscopic properties of materials, these methods which are valid for ground state are not applicable. there are a wide range of methods that are available. Our group is really interested in pushing the limits of methods that use many body perturbation view. To give you one example, if you're interested in understanding tunneling experiments or Arbus experiments or even light matter interaction, one can typically restrict the problem of adding one particle or one particle and one hole to the system. For tunneling, for instance, problems one has to solve an equation of motion that looks like this for the positive particle energy. The challenge is that the effective potential that each particle feels is now dictated by the self-energy, which is a non-local energy dependent on non-emission a problem that basically describes the interaction with your system. I have one more slide that at least tells you the importance of dealing with methods such as this to describe excitations as opposed to using a simpler mean field theory such as density functional theory. And for me, the simplest and clearest example is that of the optical absorption spectrum in materials. And this is actually particularly dramatic in 3D materials. The reason is the following. If you naively say that if you shine light, you just create a free non-interacting electron, non-interacting hole, as shown on the left hand here, and we often call this RPA or random phase approximation, you basically get an absorption spectrum shown here in red, which is basically the joint density of states of excitations. We can treat the material as just a step function. This red curve doesn't even qualitatively agree with the experimental measured absorption spectrum by Tony Hines in the 2010 in this earlier pioneering work. What we're missing, of course, is that if you shine light, you don't have a free electron and a free hole. The electron hole form a correlated or bound pair, which is known as an Electrons. There was an equation of motion for solving for them, similarly to the one that I described before. And if you solve for this equation of motion, you get this green curve over here, which is now characterized by sharp peaks of bound transitions. And right now, we can even formally include dephasing and decoherence from forms. And if you do that, actually, we get actually a very good agreement with the experiment for the overall profile, binding energy, meaning the energy associated with electron pair, and the nature of higher excitations. I do want to mention briefly that what is really exciting about these new computational techniques is that in the last decade or so, we're really being able to push that to much more realistic problems. So I have a plot here that shows that what is the maximum sort of system in terms of number of electrons that we could solve historically. And in the last 10 years or so, we increased that from about 100 electrons to now over 10,000. So we can really right now simulate much more complicated materials, such as defects in semiconductors, while accounting for all these many body, many electron interactions. It can be qualitatively even dictating your final results. I just want to move it up. I can also try to direct my voice to the mic. But basically, there are two main questions that I want to address today. The first one is how we can predictably understand all of those emergent excitations from X and so on in complicated materials, such as those moiré systems that we talked about earlier. And the second one is how we can even push the limit of our formulas to understand not only materials in equilibrium or positivity, but strongly driven systems by light, for instance. And if there are some interesting also quantum aspects in those excitations when you can account for those driving fields. So that is basically set the tone for my talk today. I'll talk about two projects that we recently worked on. The first one is a collaboration with the experimental group of Tony Hines and Prashad. Tony Hines at Stanford, of course, and Prashad at the Optical Institute of Science and Technology, where we obtain information about excitons that are localized in moiré materials, and we can have really new insights into the localization and whether these excitations can be used for film information science. So, before I talk about this, let me tell a little bit of how those excitations and excitons in particular, they look in twisted materials and bilayer materials. So we're particularly interested in classes of 2D materials called transition matter glycogenets. They are layer materials. They have a hexagonal structure similar to graphene, but with a finite thickness. And what is interesting is that when you stack two of these materials together, particularly to the similar materials, you often get a staggered band gap as shown on the left side, which means that after any initial excitation, eventually the hole and the electron may be on different layers. Because the electrons and hole are spatially separate, it means that all those excitations have a small dipole coupling to light, which means that they typically are very long lived, of the order of 100 nanoseconds, much longer than, say, what you have in a monolayer. And that, of course, means that if you have a bosonic excitation with a long lifetime, it can be potentially quite interesting for quantum applications. Now, another important aspect of those excitations of these materials is that when you stack two layers that are similar, or if you stack them with a finite twist angle, you get a moiré pattern, as shown here on the top left panel, which you probably heard of quite a lot in the series and in the last few years. So I won't go too much in detail about this moiré pattern. But I do want to mention that at least in first order, the way that I can rationalize the effect of the moiré pattern is the following. If a moiré pattern is large enough, the different local environment of the stacking of the two layers is such that locally the bandwidth is varying. At least you can understand this in terms of this. You can define an effective moiré potential by the variation of the bandwidth, for instance. And depending on the high symmetry stacking that you are, the label here is RHH, X, and AM, also from over here. Now again, a different effective potential. And of course, if you shine light and create an excitation, such as an interlayer Electron, for instance, eventually those may be trapped in those or localized and confined in those lower energy stacking configuration. And again, could be quite useful for those quantum applications and localize them and understand their localization. Again, a lot of excitement about those excitations. They're long-lived, they're boson-like, and they are spatially localized. The question is, do we know if this picture is actually correct? And it turns out that we don't have actually a lot of direct evidence. The best evidence that we have is this. You basically shine light, and you measure the photoluminescence, or in this case, it's actually the reflectivity on exons that are intralayer, but the physics is quite the same. If you have a large twist angle, your moiré pattern is very small, which means that there's not going to be a lot of fluctuations in moiré pattern, which means that you have sharp peaks associated with excitation of different layers. And then if the twist angle is pretty small, they actually get a number of peaks, which people have associated with the presence of basically different subbands and other details of those excitations. Yes?
Intuitively, would the lifetime be longer at the space where there is no overlap, or where there are like RHH versus RMH? Where would the lifetime be longest?
That's a great question. So there are two aspects that influence the lifetime. One that I just said is quite correct, in that if the interlayer distance varies, then the recombination rate can also vary. You may think that nothing's going to affect because the electron hole already separated, but you still have a tail of the exponential part of the wave function that overlap. So actually, even if you apply an electric field, you can slightly change those tails that can affect the lifetime. So that is an important effect. The other one is that depending on the high symmetry point that we have selection rules because of the local symmetries. Basically, the way that the orbitals look like may be such that some transitions are forbidden. That tends to be the most important effect of those order, the local selection rule at sites.
Okay, so the RHH, or the one with the highest symmetry, it has the longest lifetime because the recombination is forbidden.
So both these three are actually high symmetry in the sense that you can define a well-defined stacking where the layers are exactly nearly aligned to each other or offset by a fraction, a high symmetry fraction of your unit cell lattice vector. So both this are typically called high symmetry stacking, but which of them is actually dipole forbidden or allowed for those excitations are not, it's not something that is necessarily trivial or intuitive. You have to look at how the wave function looks locally at each of those.
Is there an intuitive way to think about why these excitons are localizing high symmetry stacking and at the same time in different layers?
That's a good question. So they will be localized in different layers because the first order, the most important physics is this band offset, which is large. So we typically think that the moiré potential is a smaller effect, its local variation of the stacking is smaller than the band offset between those two materials. So that's number one, why we think that the moiré potential is often a good way to rationalize the localization and why they stay separated between the the second part of your question was why the potential is moved between those points, right? Or why it's a minimum isometric point? What was it?
I guess I was thinking whether we could say to minimize its energy, whether we can have say your hole on the highest energy point.
Yeah, I see. That's a wonderful question, and indeed it is true. So this basically what you're saying is even beyond this model, people are addressing this right now. For many materials, however, the electron hole interaction is strong enough that even if the electron wants to be at another site than the hole, they just want to be on top of each other because that maximizes the Coulomb attraction, and that can often wash out any other local variation of where the electron will be. So the way to think about this is that these exponents have typically a binding energy of about 200, maybe 300 electron volt, even if this is standard. And this moiré potential may have a bandwidth of 100 MV, so a bit small. Yeah, great question. Feel free to interrupt me or whatever. I guess then we'll be allowed to use that after 15 extra minutes, right? So, no, the question I'm trying to bring is, if there's a better way that we can actually understand really how those exponents look like, their internal structure, which is more informative than basically looking at splitting of peaks in photoluminescent experiments. So, one way that one can do that is with the state-of-the-art and very recent time-field ARPS experiments. And to tackle that, let me tell you how one can actually learn about exponents from ARPS. I guess you're all familiar with ARPS, where it's a photon emission spectroscopy. You shine light, you yank out electrons, measure the energy and momentum of the final electron. You probably also have seen what an exon looks like, but maybe remind me, an exon is a correlated motion of electron flow, which means that it can describe in the reciprocal space as a linear combination of vertical transitions, or this AF pace and expansion coefficient. The question is, what happens if you shine light with an excitation like that? So if you shine light, you're gonna measure some photometer electron. If you measure a photometer electron with one particular wave vector, it means that your wave function is collapsing in one particular state and is leaving behind a hole with a volatile energy. So importantly, if you measure an electron with larger momentum, you're leaving behind a hole also with a larger energy, and hence you have less free energy for the measured electron. So that may be counterintuitive, but actually what you measure in an experiment is a negative dispersion. Because if you see in the detector that you have one particular electron, again, a larger momentum, you're leaving out more energy into your material, hence you have less energy for the measured electron. So the hallmark that have been predicted in the past is that the signature of an exon in the material is actually that of a negative dispersion. That has to be exactly parallel to that of a valence symbol to band space. The other important aspect is that the width they measure of this distribution is actually related to the width of this electron correlation, which also gives you the Bohr radius, the inverse of the Bohr radius of the rest. So there's actually quite a lot of information that one can add. Actually, last year, with the group of Chardin and the Optical Institute of Technology and in collaboration with Heinz and Pete South out of Washington, we actually managed to measure this dispersion for the first time. And indeed shown that you have this long predicted negative dispersion, which is a hallmark of an exon as opposed to free carrier system. Okay, so this is all very interesting. It was done for a moment later. And the question is, what kind of additional information can one obtain in a moiré system, especially related to that confinement physics that was described? So to address that, I have to go back a little bit and tell you a little bit more how this dispersion looks like if you have a moiré system. So as I just argued, if you have an exon, and for simplicity, ignore any moiré effect. If you have an exon without confinement from the moiré potential, with exactly zero momentum, and of course describe that as a linear combination of conduction states and valence states weighted by some coefficient use theory. Extons, just like electrons and other particles, they also have a well-defined dispersion relation. And the question is, how does the wave function change as you change the momentum? So it turns out that if you are interested in exon with a finite momentum, you basically shift the electrons around, you shift the center of the holes around, and you can perform a similar linear combination, but now with a finite momentum. And importantly, the amount by which you shift the momentum of the electron and the hole is not the same. It actually depends on the effectiveness. So if you have a flat band, of course, it doesn't cost a lot of energy to move the dispersion or the distribution for the gamma states, for instance. This is actually a very important result for piece of physics. And that's important because we can describe a moiré or an extron that is confined in a moiré potential by a linear combination of these states with different momentum. So basically, you can describe a extron that is confined in the system that is spatially localized by a linear combination of otherwise unconfined extons with different momentum. And of course, if you create a wave pattern in P space, we are also creating a wave pattern in this space. So you end up with something that looks like this. And importantly, this unconfined exon is again described as this AFA that I mentioned before. And you create a moiré exon by making a linear combination of unconfined exons with some coefficient CL. What is very important is that those two coefficients, AFA and CFG, directly give you the physics that we're interested about. This coefficient AFA is related to the border radius, the separation between the electron and hole. The CRP gives you the localization of the exon inside your molecule. And hence the point I want to make is that if you have the knowledge of those two distributions, or rather, you can measure the distribution of electrons and holes in the system, which in general, you can infer how much AFK and CRP, and from them actually get the whole information of the localization of those situations. So the question is, how can we obtain that? Of course, we can obtain that with the same kinds of Arps experiment that I mentioned before. So this recent paper, also collaboration between Heinz and Chablan, we did an experiment in a biolayer of tungsten disulfide and molybdenite. I'm showing the left-hand side of the Arp spectrum for the unexcited sample. If you pump it and measure the spectrum, you get this curve here on the right-hand side. You can clearly see some dots over here, which means that your photo-emitted electrons that are attached to the exon. But if you carefully look at this picture, and maybe I can turn on the light for a second. Let me zoom in for you a little bit. Can you see that something here? They're missing electrons. With this recent experiment, really exciting. We have information about the holders. And that was unprecedented before. You really need a lot of very good resolution, signal to noise, and so on. The point I'm going to make is that with this recent experiments, we can indeed learn about the electron and holes signature from next. Okay, so how does that connect with our theory? How we can understand those extons? So just briefly mention that if you want to understand what is the signature of the photon emission from the electron, you can just use Fermi's Boner rule. It's basically you have an initial state that is an exton. There's some interaction between Hamiltonian, some A of T. You leave behind a hole in the system. You measure the electron, and that's the final state. And perhaps you integrate over some energy range, and you get the distribution that I just mentioned last time. You may think that the hole is similar. It should be just a replica of the electron. But if you think a little bit more, you realize that it's not. It's actually quite different. The signature of a hole is such that you have an exton, you shine a light, and either the initial exton doesn't do anything, and you just leave behind a hole and measure an electron, or the initial exton captures the hole that you left behind. The other hole was left in the system, and you measure this photon-emitted electron, and those two dielectrics have to be added, and then square the return. So it looks like it's much more complicated, but actually, if you work out all the math, the final expression ends up to be nicely simple. And interestingly enough, you actually get a direct understanding of those excitations. In particular, we can show that the electron intensity is related to some convolution of that C of G that gives the center mass localization of X, and then A of K, the internal electron separation, and likewise for the whole. With one important difference is that alpha and beta coefficient that I told you that is related to the effective mass, they're different. So what our theory actually shows is that if you measure the electron and hole, you can convert those equations, you can know the effective masses, and then actually understand A of K, C of G, and get the whole picture of how maximum is. Okay, so let me show you the first calculation that we did. We essentially did, we first look at a system without moiré effects, because that doesn't affect much the internal radius. We did first this calculation, and the result is basically shown here on the bottom. If you fix the hole in the top layer, you can ask yourself, how does the amplitude of the wave function looks like for the electron? It looks like this. You actually found that we have a Bohr radius of about 2.4 nanometers for this sort of interlayer X. You can do the same thing for the center of mass problem. We use a modified parameterized DFT population, but in a sense, you have to solve an equation of motion for those moiré confined extons. And describe that in terms of a free exton, some kinetic energy terms, and some potential, the one that I just spoke before, that actually looks like this blue curve in the actual system, where I'm showing repeated supercells. If you solve this, or rather, you can write a solution as a linear combination of three extons with those CG coefficients that I just mentioned, and the result in the Fourier transforms look like this. So the exton is fairly localized. In fact, we compute that at the localization of about 1.3 nanometers, which is quite striking, actually. In fact, it's more localized than the Bohr radius. For a while, we thought that that couldn't be the case, but if you think a little bit about that and the effective mass, it's fine, right? If you have a hydrogen atom, the proton has infinite mass, you can easily localize the position of the atom much more than the Bohr radius. So we use this sort of theory and understanding compared with the experiment. And the experiment, they can measure the electron distribution, the photoemission signal for the electrons attached to the exon. And also from the holes attached to the exon, you get those two curves, you get some widths. And by basically converting those equations and so on, then you can basically get this width of the order of 1 nanometer for the confinement and about 2.5 millimeters for the Bohr radius. So yeah, we're actually quite happy with the result. There's no fitting parameter of the experiment. It actually shows that this interlayer exon is indeed quite localized. It's actually even more localized than its radius, as we discussed. So again, we're actually quite excited about the results. We have a way that we can directly deduce all this localization of those quantum excitations. And I think that one interesting result of this is that it really shows that you can, in principle, use those exons really to create an array of localized bosons, which could be quite useful for quantum theorists and qubits, because they're not going to be strongly interacting. And in fact, an important result is also that we don't need a moiré system with a very large unit cell to strongly confine those excitations. In the past, it was thought that one has to go to a 20 nanometers or so moiré unit cell. The problem is that the strain field becomes less homogeneous and so on. But actually, even with this system that has a moiré lattice parameter of about 5 nanometers, we still have strong localization and hence more robust array of elements. So I hope that it convinced you that it was an interesting fraction. And with that, I basically end the first part of my talk that I'm going to discuss. And I'd like to go switch topics a little bit and deal with systems that are explicitly driven. And I'll tell a little bit about a new excellent Flowcase physics that we're quite excited about. So the motivation for this second part of the project is the following. There's of course a lot of interest in driven systems, well, whether you can change from direct point to wire points by just shining light. Of course, you can also have structural phase transitions that understand photocatalysis and other relevant chemical applications. And basically, the state of the art is to use DFT or a time-dependent version of DFT, which is can in general capture the motion of ions to a typically satisfactory amount. But of course, DFT is a ground state formless, and it's very hard to include exciting states in it. Many-body perturbation theory, the one that I just mentioned that we used in the past, is indeed quite powerful for excitations, but it's really usually for materials in equilibrium or quasi-equilibrium, not for strongly driven systems. The question is how we can combine those two methods or develop another method for non-equilibrium, strictly non-equilibrium systems. I have 2 slides at least to give you a sense of what goes on. You have to understand, of course, the details. But the idea is the following. It is possible to do many body perturbation theory that people typically do. It's systems that are non-equilibrium. The only important thing is that if you want to do that, you cannot do perturbation of real axis. The reason is that perturbation theory relies on the fact that you're adiabatically turning on and off a perturbation, and your Slater determinant at t and negative infinity and plus infinity is the same. This breaks down if you apply a pump and you have a system out of equilibrium. So you have actually to work in a complex spring. You start with perturbation negative infinity and go back in time, and then you use the regular articulation theory and so on. When you put that actually in your pencil and actually do the calculation, it's actually much more complicated because those complex conference break down into a couple of integral differential equations. And one has to deal with basically functions that describe occupied states, unoccupied state, and the couple. So there has been a lot of interest in those equations known as unoccupied beam equation, but it's very hard to describe real materials. So what I mentioned is that we have a way that we recently put forward that you can actually use to understand real materials under modulated these driving views. We call this method a Diabatic GW, and that's because GW is known in the field as one of the approximations for the main electron interaction. So I want to mention that this approach is the following. Basically, do your many-body perturbation as usual, and you only propagate the change from equilibrium with this approach. But the change in the equilibrium we do in a way that doesn't have memory effects. That basically allows your equation of motion to be much simpler. You have a single equation of motion that has to propagate that only depends on what is known as the single particle density methods. So at the end of the day, you can rigorously show that under this approximation, you have basically a single equation of motion for this density matrix that you have to propagate, and involves some equilibrium quasi-particle Hamiltonian, the one that you can usually compute at equilibrium. There's some change in that interaction. Called this adiabatic change in the self-energy, which is the term that computes the electron-electric interactions. And you can put an arbitrary external field, this E dot R, that allows you to understand the coupling with light or even strong right fields. At the end of the day, you have an experiment you want to ask what is the optical absorption spectrum of this material or so on. And those are all readily available. You basically compute the polarization as a trace of your density matrix times the position operator and so on. So basically, you are really doing a virtual experiment by putting in the field of whichever shape you have and measuring and computing the response function to this. I want to mention that this is, of course, much more doable and practical, and we can actually obtain directly nonlinear optical phenomena that is otherwise not possible with the other approaches. Okay, that's the brief introduction of this methodology that we just want to give you, and now I'm going to give some results. The first calculation that we did was for a monolayer material, monolayer germanium sulfide. It has a structure shown here on the bottom, a band structure shown here. There's very strong many-body effects, which you can appreciate by the fact that this GW, namely the band structure computed with many electron interactions, is quite different from the one from PFT. If you use all this many-body formalism for equilibrium, the one that I showed you before for molecular sulfide, you get this red curve over here. It's quite different from the one without electron interactions, the blue one. Similarly, because this is a 2D material, you have strong many electron interactions. And if you use a new method, we call this time-dependent adiabatic GW, and you apply a weak enough external field so that you are in the linear regime, you actually get exactly the same result as you get from this other approach, which really shows that it strictly gives you the same spectrum before, including many body effects and so on, with the advantage that now we can go beyond in response and beyond group. So let me tell you some of the things that we computed. computer, for instance, second harmonic generation coefficient for those materials. Those are the things that are quite hard to compute, including all those many electron interactions, unless you use this real time formulas. Blue curve is the one without interactions. Red curve is the one with interactions. Second harmonic generation may increase by up to 1 order of magnitude, depending on the polarization direction and energy that you're considering. So really, all those effects that have been so far neglected are quite important for linearities of those materials. We're actually also very interested in what is known as shift current conductivity, or bulk photovoltaic effect. Mainly, there's an effect where you have two photons, one energy omega and the other negative omega, and they constructively give you a response that is DC, basically at omega equals to 0. And this sort of phenomena is particularly interesting because it can give you a finite current without a PN junction. So as an alternative to a traditional PN junction of photovoltaic device. In this sort of material, we can also see that this particular shift current conductivity is actually pretty large. It is enhanced, as a matter of fact, by 1 to 2 orders of magnitude, depending on the frequency they have. And that's all because of those many body effects that we just mentioned. And in fact, in those two materials, as the amount of bulk photovoltaic effect we have is comparable to one of the best known barrier-based compounds that is known. So again, we're actually quite excited about being able to predict and discover new materials with strong nonlinearities for a number of applications. Now, last topic I want to mention regarding this is that we can actually revisit the topic that we mentioned before, which is if you have a times of Arcus experiment that you shine light, you yank out an electron, and you basically see some downward dispersion. And the reason is that we're actually interested in looking at what happens if you start pumping it at a higher and higher fluence. So if you have a large X population, are you going to see some interesting effects, X1 interaction or some other many physics? So I'm going to skip the details of how we do the calculation, but this is the pitch that I want you to have in mind, this lower right panel. We can, in our calculation, put in any electric field, E of t. As the electric field is being pumped into your system, your system develops some microscopic polarization. It is also time dependent because it has some excitation at a particular frequency. And because of that, basically all the electron-electron interaction that is captured by this self-energy signal, it also requires some time dependence. So all those two effects happen and you can actually describe as you apply this external E of t. So we talked before of what to expect in times of Arcus. We have this linear combination of electron pairs. If you shine light and yank out an electron, leave a hole behind, you should expect negative dispersion. And you can understand that actually, not even quantum mechanics, just energy conservation. That's enough to understand this downward. I do want to emphasize that you get this negative dispersion without having an external pump. Basically, even if your pump is off, you should see this sort of signature. And the interesting aspect is that if you do exactly simulate this, you don't include many electric interactions, no many body effects. You only see a simulation of the time result Arcus of the occupied state. There is nothing in your system because, of course, you cannot describe X. If you do a simulation with electron interactions, you pump exactly at the X resonance. What do you see? You see a downward dispersion exactly as we predicted in the test, or exactly as we have shown in the test. Of course, it's good, it's reasonable. But what we can do now is keep cranking up the fluence. And we'll still have still have this negative dispersion. But you can see there's something funny going on over here. It's not that parabolic dispersion. In fact, to zoom in, you can see that you have a camelbacking like behavior close to this valence band maximum. So the question is, what is the origin of this band minimization? Is there anything interesting or new about this? So first of all, I want to mention that you can measure this band normalization. It increases with the fluence or the intensity of light. So if you look at this new curve, if you pump exactly the X resonance, you can have up to larger than 100 MeV for experimental accessible fluences. In the past, actually, people have computed this and predicted. They have interpreted this, however, as a non-equilibrium axion condensation. So basically, there's a one-to-one mapping between system out of equilibrium and an axion condensate. What is an axion condensate? It's a system where the bandgap is small enough that the axion binding energy is larger than the bandgap. What does that mean? It means that for the system, it can actually lower the energy by creating one axion. Because the axion takes less energy to create than the bandgap. This is not a true axion insulator, of course. It is a system that is a regular semiconductor. You just have a large axion population. But they claim that the signature of this Campbell-Beck and Swan is similar to that on those more exotic condensates and insulators. So we basically want to ask whether that is indeed the case, or whether there's a simple explanation or simpler explanation behind that, because arguably non-equilibrium axion insulator is not a particularly elucidating way to think about those scaling normalization of those systems. So here's what we do, and basically 2 slides you can understand this new way to understand the students. At the end of the day, all of the observables that we can understand are given in terms of that single particle density matrix rho. We have some equilibrium part of your Hamiltonian, I'll call this energy K and CK. There's some external pump. If I do the measurement after the pump is gone, I can ignore that. And of course, I have some electron-electron interaction that's captured by the sigma term that I mentioned here, that self-energy. The self-energy is generally a matrix as well. There's going to be something that couples the electrons to poles, and something that is diagonal as well. What is the main important aspect? If you have a number of axions in the system, those axions will be oscillating at a frequency E sub x, or E sub x is the axion energy. And that means that your self-energy that captures the coupling between electrons will also be time dependent. So if you look at this Hamiltonian, you can think of this as 2 levels that are non-interacting, and there's going to be some coupling that is time dependent. What happens if you have a non-interacting system and you put into some time dependent coupling? That is known as Flowcases. Whenever you have a perturbation that is time dependent, you can actually allow for hybridization of states that are separated by some energy. Flowcase is actually, or block Flowcase is nothing else than a traditional Bloch's theorem applied to the time domain. So what is Bloch's theorem? You say that if you're breaking the translational, continuous translational symmetry and invariance in plane, states that are separated by a reciprocal lattice vector, 2 pi over a, can couple. Same thing goes here. If you have a time dependent perturbation, 2 states which are separated by 2 pi over t, where t is the period of your perturbation, can couple. 2 pi over t is exactly the frequency they put in. So basically, the Flowcase theory said that if you have a state, for instance, and this is applied by Mugabe and collaborators, if you apply a pump in it, we're going to have replica states that are separated by 1 additional or 1 fewer photons, and they can all hybridize. Our Hamiltonian looks exactly the same one as the Flowcase, so we can actually write and solve it using exactly this Flowcase kind of theory. Basically, a conduction state hybridizes with a valence state that is replicated by the axion energy, or vice versa. A valence state is hybridized with the conduction state with some that is displaced by some energy, and the coupling is basically the Fourier transform of your self-energy, basically. So this effect looks exactly like Flowcase, it's the same physics, but it's not caused by light. It's caused by some other field, some other bosonic field, the bosonic field from the X. So we call this a self-driven X Flowcase effect, because it is indeed caused by the presence of your excitations, and it does not need any kind of probe overlap. The question is, does it work? On the right-hand side, we show our formalism by using this Flowcase kind of picture. It is exactly what you expect. Basically, you have a valence band. You have that negative dispersion from the X that I mentioned before. And actually, you can understand the negative dispersion as the replica for the valence state, exactly the replica for the Flowcase theory that I just mentioned before. Likewise, you have a conduction state that I'm not shown over here. You have a replica of that conduction state over here. And the conduction state replicated and the valence state will hybridize and lead to those Campbell-Beckman features. So basically, what we've shown is that we don't need to talk about non-equilibrium Electron policies or anything like that. What happens simply that if you have a large Electron population, you have Flowcases, and the Flowcase is driven by the Electron itself. We explain all of those replicas that have been measured in the experiment. It's actually an alternative way to think about that. And for free, it also explains all those many body linearizations. So we're quite excited about that. It looks maybe a little bit abstract, but there's a lot of ways that we can engineer materials with light and shine light by, again, from direct point, electrons. There's a lot of research, for instance, group of Tom Weber over here at Stanford, of how you can engineer phase transitions, topological states, chiral edges in regular materials by simply shining light. So I hope you're convinced that this can be a very attractive and alternative way to engineer those unusual phenomena without necessitating necessarily a very strong and transient light process. So with that, I'd like to go also conclude this part of my talk where we describe its formulas in computer materials and real materials out of equilibrium. Of course, there's a lot of enhancement of all those conductivity cancers that include those many body effects. And we are also excited about this picture of this excellent feature. So with that, I finish the two parts of the talk that I want to mention. Since I've also been here on for 2 years, I do want to maybe make sure that you know other things that our group is interested in. If you're also interested in other collaborations, we're quite interested in moiré systems and beyond moiré, either with more complicated materials, more layers, and even ditching those continuum autos and doing all calculations optimistically, as shown here, for instance, on this top right. We're also interested in defects, how the centers for quantum information application, how we can design ways that they can be tuned and detune from an environment for specific applications. And another direction that I started here at Stanford, much more applied, but I'm also excited about, is how we can use those excited states actually for renewable chemistry. So for instance, instead of doing, if you have a system such as a proton next to a surface of titanium, you can compute a potential energy surface for that atom moving wave. But if you actually have the system in the excited state, missing one point over here, this point over here, I would be able to convince you that if you have exactly the same system in the excited state, the barrier is much smaller. So there's the opportunity to drive reactions that are otherwise not possible in the ground state. And really, you can think of exciting the system as another tuning out for chemistry as opposed to just changing pressure and concentration of different gases. I also want to thank the Acknowledgements current group members right now. And very importantly, I want to acknowledge the main authors that were involved in this collaborations. Hao, Diane, and Chu, and Stephen Lewis, specifically for the Flowcases work, and some of the earlier work with the Electrons. And my student, John Diabatic, was the one involved in the confined moiré Electrons. Of course, the group like Bishop Lenny did this very beautiful work with angles of Artis. Of course, the group of spectroscopy of Tony Heinz, Elise Lorraine, and Uri Carney, and all the other grad students and postdocs that have been quite important for this work. So I also thank you all for your attention and be happy to address any other questions that you have.
Thank you. Questions? And people on Zoom, please feel free to ask questions also. Unmute yourself if you'd like to answer. Go ahead, yeah.
So thank you for the excellent talk. And I guess I'm wondering from the perspective of tailoring and engineering materials, do you feel that there's a straightforward way to tie phenomena like atomic reconstruction or twist angle to these properties like exciton lifetime? or confinement of excitons. In other words, these empirical relationships, is there a way to straightforwardly represent them?
That's a great question. I think that there is indeed. You should look back and ask yourself, why are TMDs so good for all those applications of interlayer excellence and so on? It's not a coincidence. There's something very special about the wave function. You can actually use the board. I feel like the whole room. Nope, not here. No. So, simulation for people who join the Zoom in person. So on those materials, the valence band maximum and conduction of the minimum of a single layer is at the K point. And what is special about the K point? Well, what's special about the K point is that if you look at a single transition metal electrocoordinates, you have the transition metal atom, it's called M in the middle. You have some components such as sulfur or selenium sticking up or down. So what is really special about this material is that the wave function at both the valence and the conduction band is actually fairly localized in the middle of your system. So it's really that the low energy excitations is such that there's not a lot of interlayer hybridization for many of those settings, and that allows for all those excitations to be particularly long lived. Of course, in some systems, the valence band maximum, for instance, is at the gamma point. The gamma displays much more hybridization all over the place, and in that case, when you stack two layers, say even a homobilayer layer, for instance, you don't have the electron hole separated, the lifetime goes down dramatically. So there are a number of implicit rules that are related to the wave function too that are quite important. But what you're alluding to is really quite important as well, which is can we go beyond those transition metal electrocoordinates and look at a broader phase space of materials that could be interesting for moiré phenomena. I'm quite interested about the direction, but I haven't seen much going on in the literature.
Yeah, thank you totally a little bit. Any other questions? Go ahead. Yeah.
I'll ask one question about comments on options. So you can see the excitons, if the excitons are trapped in local moiré traps, that's in the longer periodic structure, would you also expect to see the electrons in the host to be appearing in a different momentum, like the backfolded structure from trapped waves?
Did you see? Do you mean, for instance, you have a large moiré unit cell, and whether even the electron hole are separated by a momentum space, or
if the electrons in the host are trapped in the longer periodic moiré unit cells, in the momentum space, would you expect them to show up in a different momentum than the original momentum from the small unit cell?
Yeah, that's a great question. In general, yes. There are two ways, however, how this can be manifested. So, of course, if the electron hole are tied to each other, just moving around the unit cell, there's just a phase, right? There's no hope anyone can get the phase times of darkness. But if you have a large moiré period, such that the electron hole can be spatially separated in the incline direction, and we actually have some calculations that show that many systems support that, then the different separation in the incline direction would correspond to some difference in the width of the electron hole that one can also deduce from times of darkness. Yeah, so that should be possible. Any other questions?
Yeah, sorry, another question. There's been a lot of excitement in these moiré materials based on the emergence of ferroelectricity between layers. Can you comment on how that might relate to your calculations? Is this something that's easy, or is it automatically incorporated, or do you have to add it in as an additional potential term?
That's a great question. The main idea of computing through electricity is not very different from what I mentioned. So, for instance, if you have a twisted HBM, for instance, and then you say alternating for electricity that can induce a more potential in a nearby layer, that is in fact something that we can and are interested in sort of question is, one can basically simulate directly the system on a large unit cell with a HPM and a bilayer or monolayer, and simply ask how the local environment is changing with a very similar technique, the one that we just mentioned before, and that you can locally compute how the bandgap is changing. Right now, of course, the bandgap will be changing because of this alternating ferroelectric domain. There's some questions that need to be a little bit more carefully addressed that people haven't looked into, which is, for instance, interplay between relaxation effects on any adjacent layer to the ferroelectric domain, and also what is the extent of the field, not only being a field that is applied in the high symmetry point, but also basically fringe fields and other phenomena, how that can be some degree smooth out a little bit more. But no, those are all, I would say, straight, relatively straightforward with the same methods and approaches.
I have one quick related question on the same topic of being able to compute a larger moiré unit set. Often with the as experimentalists, we realize that the theory does talk about the ideal case, but when we make the sample, it's really disordered, and there is a lot of local variation, perhaps in the scale of tens or maybe hundreds. In reality, when simulating some of these things, is it possible to how large a gradient set can we simulate that, and can we introduce disorder into these systems and see effects?
Great question. And actually, that's precisely why we're excited about the smaller unit cell, because then, of course, we have less variability because we have strain fields and effects like that. It really boils down to what level of sophistication and what kind of physics needs to be addressed. So, for instance, those continuum models tend to scale very well to large systems. We have ways and we have ways right now with classical force fields that were parameterized to DFT calculations to actually capture the effect of later consortium. Actually, let's have a slide there. But essentially, you can account for more or less straightforward a moiré effect from very large and disordered unit cells. The question is a little bit more subtle on what is the effect regime. Of course, if your unit cell is large enough, then you wouldn't think that you have a moiré localized axis. You just have a large domain and have a domain. Of course, those are related to the other particles that are coming into play, such as phonons or even finite temperature effects. And the final question is, to what degree is the one coherence enough to give you a moiré localized axis? And I think that this interplay of when we have moiré axis, when we have a classical boundary in a material, and when we have enough coherence, it hasn't been addressed satisfactorily so far. But to various degrees, I think that one can simulate disorder, simulate effects, but either extreme cases as opposed to a smooth position.
Any other last minute questions? Okay, let's thank Professor Jornada once again. Thank you all for the Zoom attendees. Yeah.